this module, you will learn about the Carnot engine. Much before the concepts of thermodynamics were established, Nicolas Leonard Sadi Carnot, a French physicist, proposed a hypothetical ideal heat engine that works with maximum possible efficiency. A hypothetical reversible heat engine operating between two temperatures is called a Carnot engine. To get the maximum possible efficiency, all the processes involved in the working of the Carnot engine operating between two temperatures must be reversible. Since all the processes are reversible, there will be no dissipative effects. We know that a process is reversible only when it is quasi-static. In a quasi-static process, the system will always be in thermal and mechanical equilibrium with its surroundings. There are two processes in which a heat engine exchanges heat with the surroundings. In one process, the heat engine absorbs heat from a hot reservoir at temperature T1. And in the other process, it releases heat to a cold reservoir at temperature T2. Since the system must be in thermal equilibrium, these two processes need to be isothermal. There must be two more processes. In the first process, the temperature of the system changes from T1 to T2. And in the other process, the system is taken back from T2 to T1. Since there is no exchange of heat involved in these two processes, they must be adiabatic. The cycle of two isothermal and two adiabatic processes through which the working substance of a Carnot engine passes is known as the Carnot cycle. Let us now discuss the sequence of steps involved in each Carnot cycle. Consider mu moles of an ideal gas in a container with a movable, airtight, smooth, frictionless piston as the working substance. Let the walls of the container and the piston be made of thermally insulated material, and the bottom of the container be made of diathermic material. Assume that the initial state of the system is P1, V1, T1 and is identified by point A in the PV diagram. Note that the gas is in a compressed state because of some tiny weights on the piston. In the first step, place the container on a hot reservoir, which is at a constant temperature T1, and slowly remove some of the tiny weights one after the other, and allow the gas to expand isothermally. During this expansion, let the state of the gas change to P2, V2, T1, which is identified by point B in the PV diagram. Let the heat absorbed by the gas be QAB and the work done by the gas be WAB. For an isothermal process, there is no change in the temperature of the system, and hence the change in the internal energy is zero. Therefore, the heat absorbed by the system is equal to the work done by it. Therefore, for an isothermal process, the work done by the system WAB is equal to mu R T1 ln V2 by V1. Let this be equation 1. In the next step, the container is kept on an adiabatic platform. Now, by removing some more tiny weights, one by one, allow the gas to expand. Since the gas is surrounded by adiabatic material, there can be no exchange of heat between the system and its surroundings, and hence the expansion is an adiabatic expansion. Let us assume that this adiabatic expansion has taken the system from B P2V2 T1 to C P3V3 T2, and that this is represented by the BC curve in the PV diagram. For an adiabatic process, heat absorbed QBC is equal to 0, and the work done WBC is equal to mu R into T1 minus T2 by gamma minus 1. Let this be equation 2. Since for an adiabatic process, Tv to the power of gamma minus 1 is constant, we can write T1 V2 to the power of gamma minus 1 is equal to T2 V3 to the power of gamma minus 1. Let this be equation 3. In the next step, let us place the container on a cold reservoir, which is at temperature T2. By placing back some of the tiny weights on the piston, allow the gas to compress isothermally. In this process, the system releases heat to the cold reservoir. Assume that during the process, the state of the system is taken from C P3V3 T2 to D P4V4 T2. Let the heat given out by the system to the cold reservoir be QCT, and the work done on the system be WCT. Since the process is isothermal, QCD is equal to WCD, which is equal to mu R T2 ln V3 by V4. Let this be equation 4. In the final step, place the container on an adiabatic platform once again and compress the gas by adding small weights one by one. This adiabatic compression has taken the state of the gas from dP4V4T2 to A P1V1T1. The work done on the system, WdA, is equal to mu R into T1 minus T2 by gamma minus 1. Let this be equation 5. As the process is adiabatic, we can write T2V4 to the power of gamma minus 1 is equal to T1V1 to the power of gamma minus 1. Let this be equation 6. In one complete cycle, the work done by the gas W is equal to WAB plus WBC minus WCD minus WDA. Note that we have taken the negative sign for WCD and WDA as the work is done on the system during the compression. On substituting the values from equations 1, 2, 4 and 5, we get W is equal to mu R T1 into ln of V2 by V1 plus mu R into T1 minus T2 by gamma minus 1 minus mu R T2 into ln of V3 by V4 minus mu R into T1 minus T2 by gamma minus 1. On simplification, we get W is equal to mu R T1 into ln of V2 by V1 minus mu R T2 into ln of V3 by V4. Let this be equation 7. We know that the efficiency of the heat engine, eta, is equal to the ratio of the work done by the system to the heat absorbed by the system. The total work done is W, and the total heat absorbed is QAB. Note that heat is absorbed only during the process AB. In processes BC and DA, no heat is exchanged since they are adiabatic. And in process CD, heat is released. Hence, these three processes are not considered. Therefore, efficiency is equal to W by QAB. Substituting the values for W and QAB from equations 7 and 1. And, on further simplification, we have eta is equal to 1 minus T2 by T1 into ln of V3 divided by V4 by ln of V2 by V1. Let this be equation 8. Equation 3 can be rewritten as V2 by V3 is equal to T2 by T1 to the power of 1 by gamma minus 1. Let this be equation 9. Similarly, equation 6 can be rewritten as V1 by V4 is equal to T2 by T1 to the power of 1 by gamma minus 1. Let this be equation 10. From equations 9 and 10, we have V3 by V4 is equal to V2 by V1. Let this be equation 11. From equations 8 and 11, we get eta is equal to 1 minus T2 by T1. Let this be equation 12. Hence, the efficiency of the Carnot engine eta is equal to 1 minus T2 by T1. We know that the Carnot cycle is a reversible cycle. Every process of the cycle is a reversible process. If each step of the Carnot cycle is reversed, we get a reversible refrigerator that receives QCD heat from a cold reservoir at a temperature of T2, and after work W is done on the system. It releases heat of QAB to the hot reservoir at a temperature T1. Let us now compare the efficiencies of two heat engines working between the same temperatures T1 and T2. One of the engines is an irreversible engine, I, with an efficiency eta I. And the other engine is a reversible Carnot engine, R, with an efficiency eta R. Let us start with the assumption that the efficiency of the irreversible engine is greater than the efficiency of the Carnot engine. This means eta I is greater than eta R. Let this be expression 1. If eta I is greater than eta R, then the work done by the engine I must be greater than the work done by the engine R. If Wi is the work done by the engine I, and Wr is the work done by the engine R, then Wi is greater than Wr. Let us call this expression 2. Now, let us couple both the engines, such that the irreversible engine I works as a heat engine, and the Carnot engine R works as a refrigerator. Since the Carnot engine is working as a refrigerator, WR is the work done on the system. Let us assume that the heat engine receives heat Q1 from the hot reservoir and returns some heat Q1 minus WI to the cold reservoir. Let us also assume that the engine R, which is working as a refrigerator, absorbs heat Q2 from the cold reservoir and returns heat Q1 to the hot reservoir. Then the work done on the engine R, WR, must be equal to Q1 minus Q2. This also implies that Q2 is equal to Q1 minus WR. But as per expression 2, we know that WI is greater than WR. Then we can conclude that Q1 minus WI is less than Q1 minus WR. But Q1 minus WI is the heat returned to the cold reservoir by the engine I. And Q1 minus WR is the heat received by the refrigerator. Substituting the value of Q2 in this expression, we get Q1 minus WI is less than Q2. Since Q2 is greater than Q1 minus WI, the net heat taken from the cold reservoir is Q2 minus of Q1 minus WI. On substituting the values of Q2 and on further simplification, the net heat taken out of the cold reservoir is equal to WI minus WR. Note that the coupled system has received Q1 heat from the hot reservoir and has returned the same heat to the hot reservoir. This means the coupled system is able to extract net heat from the cold reservoir and convert it completely into work. This is a violation of the second law of thermodynamics. This means our earlier assumption that eta I is greater than eta R, or the irreversible engine is more efficient than the reversible Carnot engine, is wrong. This conclusion leads us to Carnot's theorem. It states that working between a given set of temperatures, no engine can have an efficiency greater than that of the Carnot engine. It also states that the efficiency of the Carnot engine is independent of the nature of the working substance. Though we use the ideal gas equation while deriving equation 12, it must be true for any working substance. If we compare equation 12 with the equation eta is equal to 1 minus Q2 by Q1, we get Q2 by Q1 is equal to T2 by T1. Note that this relationship Q2 by Q1 is equal to T2 by T1 is a universal relationship and is independent of the nature of the system. You have now reached the end of this module. In this module, you learned that a reversible heat engine operating between two temperatures is called the Carnot engine. The cycle of two isothermal and two adiabatic processes through which the working substance of a Carnot engine passes is known as the Carnot cycle. The efficiency of the Carnot engine eta is equal to 1 minus T2 by T1. Carnot theorem, working between the same temperatures, no engine can have efficiency greater than that of the Carnot engine. It also states that the efficiency of the Carnot engine is independent of the nature of the working substance. Q2 by Q1 is equal to T2 by T1 is a universal relationship and is independent of the nature of the system.